I'd like to introduce myself. My name's Mike Bond. I'm the Managing Director of Aluminium Materials Technology Limited, a spin-out company from Aeromet International Limited. The NATEP project, which has been highly successful for us, that I'd like to talk about today, is called High Strength Aluminium Powder for Additive Manufacturing. We had a short name for it called HighSAP, and it was run. I set the project up with PSI, who are an atomizing company, Renishaw, who are one of the world leading additive manufacturing companies, and Rolls-Royce. So to run through quickly the partners, and I chose the partners in a way that was very much in line with this being a supply chain project. So we had someone who could atomize the powder, we had someone who could make additively manufactured parts, we had ourselves at Aluminium Materials Technology, who owned the patents to the alloy, and we could heat treat the material. And of course we had a end user in Rolls-Royce who were very strongly supporting it and working all the way through. The use of this sort of technique of different people but all bringing it all together was what made it very successful. So let me tell you a little bit about the background, and it's quite important that we do this. Aeromet originally invented an alloy which eventually became known as A205. Now, this alloy is aluminium, copper and 3% titanium diboride, so it's technically a very, very dilute metal matrix composite. They invented that because they are a casting company, and this was to get over the difficulties they had making another alloy called A201, which was aluminium copper but without the titanium diboride. In doing so, they actually invented the world's strongest cast aluminium alloy, and that alloy is in production all around the world on flying parts and is a major aerospace alloy for castings. We then went on to determine whether or not we could turn that into a powder, and I'll come on to the technical reasons and the problems going forward. But obviously making a powder and then additively manufacturing is a totally different technology to what Aeromet and Aluminium Materials Technology was used to. By bringing together these partners, it enabled everybody to gain from it, but also enabled us to test the material to aerospace standards. So again, Aluminium Materials Technology, patent holders, and the alloy, PSI atomizing, and you'll see a picture at the bottom of the page that shows the spherical powder obtained from a PSI atomizer. Renishaw, as we mentioned earlier, were additive manufacturing, and of course Rolls-Royce were end users. The little model on the bottom right hand corner is actually made from A2X powder, but is not a full-size engine obviously. So for any project to be successful with NATEP, it has to have several key factors, and the most important one is it is a project that brings innovation to the UK, and it's also new technology. A205 was already established as a cast material, but it had never been effectively turned into a powder. Aeromet and Aluminium Materials Technology Limited had actually made some small samples with Renishaw beforehand, which we presented at this kickoff meeting. But to actually find out whether or not this could be a commercial, viable aerospace powder for the ever-growing additive manufacturing market, we needed to bring this together. There was a lot of people who would say at the start that the addition of titanium diboride into an aluminium copper would make it very difficult to be additively manufactured. But we already knew from experience that aluminium copper on its own did not make a good additive manufacturing powder because it micro-cracked and therefore was unusable. So we used the supply chain route to look how we would do that. And it was very much done on a small scale. This wasn't research and development in the sense of running tonnage of material, but on small scale to prove the principle. And in fact, what we were looking to show was the reason that the patent was given to A205 alloy is that a unique cooling mechanism. It didn't form any dendrites, which is common in alloys, and therefore we were anticipating and trying to prove whether that unique cooling system that was a part of A205 would carry forward and enable us to make A2X powder. A2X is a trade name that we invented and still use today. So the highlights of the project. Now on the top right hand side, you'll see there is some of the difficulties. I don't intend spending any time on difficulties. There's always administration, there's always paperwork, but that's part of life. What we were really looking for, as I said before, is can we prevent microcracking? Any microcracks totally ruins it as an additive manufacturing material. And can we prove that the mechanical properties that we show in A205 cast material, which in fact is the world's strongest cast aluminium, can be translated or even improved upon in an additively manufactured powder made from that alloy. So we undertook a series of atomization trials, different chemistries, different particle size ranges, and we had test bars made at Renishaw. Those were statistically put together so that there was a reasonable number to make it valid, not just one-offs. And from there we heat treated the material. Now the additively manufactured part has to undergo a solution treatment and precipitation hardening as you would with a cast material, but that heat treatment had to be developed in detail for the AM part, additively manufactured part, as opposed to cast material, because there were slight differences and important differences found. At the end of this, I'm very pleased to say that we were able to show that the mechanical properties of an additively manufactured A2X part were higher than the cast properties obtained from the original alloy. For the metallurgist, I'll give you the details. The yield point, that's the point at which it becomes plastically deformed, was 445 megapascals. The ultimate tensile strength was over 500 at 511 megapascals. We in fact done higher than that within the project, but that was done with a change of chemistry, which is too detailed for this short talk today. And very importantly, it had high ductility at 12%. When you compare that to the cast material from which it was made, you'd have ductility 3 to 5%, and the elongation was 12%, so you can see it's significantly better. Those mechanical properties make it equal to any other high-strength aluminium powder that's on the market at the present time. And the fatigue properties that we achieved, and the fatigue properties were measured by Rolls-Royce, were actually greater or stronger than aluminium, silicon, magnesium, the standard additive manufactured aluminium powder. So we had higher strength, better ductility, higher fatigue. And when we started to look at the other significant factor that you'll need for aerospace use, which is can you run this aluminium part at higher temperatures, then we saw an even more significant advantage over aluminium, silicon, magnesium based additively manufactured parts. You'll see that there's the ultimate tensile strength. The units are on the left, the megapascals, and this is comparing what would be considered at the time the highest available high strength aluminium powder. And as you see, once you get above 120 to 150, any additively manufactured part manufactured from a base of aluminium, silicon, magnesium starts to lose its properties rapidly and cannot be used at those temperatures. What we found on the heat treatment side was we had to heat treat up to 190 degrees centigrade as opposed to conventional aluminium powders 160. And what we also found is that you can use this powder in a situation where the temperature could go to 180 to 190 degrees, a significant advantage. So the benefits to the partners are different, but I'd like to run through them because all projects should have benefits for every partnership. Aluminium Materials Technology Limited was able to prove and bring to the market from a very small trial with NATEP, and without NATEP it would have been very difficult, a powder that is already recognised in the aerospace market and other markets as being significant. PSI make atomizers for other people, and they were unable to talk to various companies who would then buy more PSI machines or do more in-house toll atomizing. Renishaw are in the top 5 additive manufacturing machines in the world, and they were the first to be able to show that A2X was viable on their machines. And Rolls-Royce as an end user require high temperature, high strength aluminium powders to be used in their engines, and this was recognised, and now it's on their strategic plan going forward. The part that you can see we're very proud of, what we all wanted to achieve, each of the partners, was to be able to walk away not with just results but with something significant. This is a additively manufactured part designed by Rolls-Royce, and each partner was presented with, and I use the word presented because we all thought it was a great success, with a 3/4 size part. That part that I've just shown you is actually hollow all through the oil ways, and would easily demonstrate that A2X powder is suitable for additive manufacturing in complex aerospace parts. The benefits to the aerospace industry, often it's difficult to actually quantify that in some way, but to actually have a UK-based aluminium powder for the additive manufacturing market is a very big win for the aerospace industry. It's also very important that the aerospace industry takes on board additive manufacturing, and they have tended to miss out on the advantages of aluminium and go straight to titanium and pay significantly higher prices and a detriment in density. So this will enable everyone within the project to work and move forward on this. The picture on the top right hand corner is a very small piece of work we've done in the project, but we're very keen on to show was all of the other results are on laser bed sintering systems. There is a need to be able to use what we call the coarse powder that's atomized, and in this instance this is an example of a laser fed blown powder system which could eventually use the higher size particles that come from atomizing. This can make the economics very much better. Just before I sign off and say who I am, how you can contact me and all those good things, the picture on the bottom left hand corner are the people that were heavily involved in it. There is one person missing, Alan Maskell from NATEP, but I'll go through them very quickly from left to right. Paul Murray is from Rolls-Royce, Tim Ward from NATEP, he's a technology manager, Gordon Kerr from PSI, myself with a rather short one there, and Martin McGann, who was Renishaw but is now actually working in my team under Aluminium Materials Technology Limited. I want to thank them for the way they worked on this project. Every single one of those turned up at every project meeting, and without everyone working in such a strong team, we wouldn't have been successful. I'd like to thank you for listening to me. My name is Mike Bond, as I said, Managing Director, Aluminium Materials Technology Limited. My details are on the screen. I would be very pleased to talk to anyone about A2X powder in the future. And thank you very much for your time.